Hello everyone. Welcome you all to NPTEL problem solving session week 3 for the course Introduction to Group Theory. I am Priyanka Sharma, your NPTEL PMRF teaching assistant. I am a PMRF fellow from Department of Mathematics, Indian Institute of Technology, Patna. So let's start this problem solving session. So first I want to summarize the topics which were covered in week 3 lecture. So these are some topics. First one is elementary number theory. So in this video, you can learn about what is LCM, what is congruence modulo M, and how we define complete residue system for some integer M modulo, and what is residue classes. Then in the second lecture, you can learn about order of elements in a given group. And if we know what is order of x, then how we can define order of x to the power d for some natural number d, and how to define order of ab. And then there are some topics like cyclic groups, what are the characterization of it, and what are forms of its subgroup. So let's cover a quick summary. So the first definition is about order of an element. So let G be a group and we fix an element X in G, then order of the element X, which is denoted by O of X, which is rated as order of X. So this is defined as order of X is minimum of those natural numbers R such that X to the power R is E, where E is identity of G. And if we can't have such finite positive integer R, then we say that order of X is infinite. So this is basically what you say, that if you have a group and you have an element in it, then the order of the element will be the least positive natural number, say R, such that if you take x to the power r, then you will get the identity element of the group. Okay. So let G be a group and x be an element in it with finite order. So if order of x is n and if x to the power d is identity. Okay. So we are saying that order of x is n, that is you will have x to the power n is identity. So whenever you will have some x to the power d is identity, then this n will divide d. Why? Because n is such least natural number. Okay. So you can say that order of x is minimum of such natural numbers. Now let G be a group and x be an element, and if order of x is again finite, then this is how we define order of x to the power some natural number d. So if you Hello. Hello.
Yeah, good evening, ma'am. Good evening, ma'am.
Good evening. Am I audible? I think there are some network issues, so the call was interrupted.
You're audible, ma'am.
Okay, okay. Just give me a few minutes. Is this screen visible to you all or no? Hello.
Yes, ma'am.
Is this screen?
Hello. Hello, hello.
No, the hello.
Yes, ma'am.
Hello. Uh,
Hello.
I'm sharing my screen from so I can share the PT. Hello. I think now this is visible or no?
No, ma'am, the screen is not visible.
Hello. Screen is not
Yes, now
visible. Uh,
it is visible now.
Now it is. Okay. Okay. But wait, this is not being scrolled. Okay. So, hmm. So we were discussing about order of elements in a group. Okay. Uh, Sorry for the inconvenience. Actually, some network issues are here, so that's why. Okay. So if we have order of order of x, and if we have order of x is finite, then how we can find order of x to the power d? This will be order of x divided by GCD of order of x and d. Okay. And clearly, if order of x is infinite, then order of x to the power d for some natural powers, this will be again infinite. Now, if we have order of A and order of B, then when we can say something about order of AB? So, if A and B commute, then we can say that order of AB, uh, this divides LCM of order of A and order of B. Okay, and in particular, if order of A and order of B, they are co-prime, then order of AB is same as product of order of A and order of B. Okay, but this is true only if A and B commutes with each other. If A and B do not commute, then we can't say anything about order of AB. You can remember we did an example in some matrix group, okay, where order of A and B were some finite numbers and order of AB is infinite and vice versa. Okay, so actually there we picked some matrices as elements, and matrices generally do not commute, so that's why. Okay, now what is a cyclic group? So cyclic group is a group in which we can find some generators. That is, we can find an element X belongs to G such that that group G is generated by X. That is, every element in G can be written as some power of X, some positive powers, I mean positive integral powers. Okay. And now what is isomorphisms? So suppose we have two groups, G and G dash, then a function phi from G to G dash is said to be isomorphism if the function phi is a bijection, that is, it is 1, 1 and on 2. And secondly, this phi preserves the binary operations of both groups. Okay, that is phi of AB is phi of A, phi of B. Okay, so just one thing I would like to mention here, this is phi of AB, this will be phi of A, phi of B. So here A and B, these are coming from the group G. Okay, so here between A and B we will use the binary operation of the group G, and here phi of A and phi of B, that is we took phi images of elements A and B, so these two will belong to the group G dash now. So here the binary operation will be the binary operation of the group G dash. Okay, so that's why I wrote here phi preserves group's binary operations. Okay.
Yes, ma'am.
Symbolically, we write it as G as isomorphism. Okay. Now this is the result that whenever we have, wait, I forgot to write it here. We can have only two types of cyclic groups actually. Okay, whenever we say something about cyclic group, so we can have two classes of groups up to isomorphisms. Okay, or we can say we can have only two kinds of groups. Uh, if the group is infinite, then this will be isomorphic to Z plus, and if the group is finite, then this will be isomorphic to Z over NZ. Okay. Other than these two classes, I'm saying classes because this second, like finite group, Z over NZ, this can be like infinitely many when you change N. Okay, so we have only two classes. One for infinite, there is only one case, the group can be Z plus. Okay, so if you have an infinite cyclic group, then that group will be isomorphic to Z plus. Okay, and if you have a finite cyclic group, then that group will be isomorphic to Z over NZ, and the binary operation is integral modulo n addition. Okay, so this will be for some fixed n. Okay, other than these two cases, you can't have any cyclic group. Okay. Now, some other important results, like every subgroup of a cyclic group will again be a cyclic group. And if G is a cyclic group, and if this is generated by X, then this will be generated by X inverse also. Okay. That is, in case of a cyclic group, some element and its inverse, they will generate generate the group like if they both generate the group or neither of them. Okay, so some other important things, like if G is an infinite cyclic group, then any subgroup of G is isomorphic to dz. Okay, why? Because whenever you have infinite cyclic group, so that will be isomorphic to Z. And what are the form of subgroups of Z? They are NZ, or we can say DZ. Okay, where this D is some non-negative integer. Okay, I'm saying non-negative because we can have 0 also. Okay, so whenever you have infinite cyclic group, any subgroup will be isomorphic to dz. Okay, and what if you have finite cyclic group? So if you have a finite cyclic group, then for any given positive divisor d of order of g, we can have a unique subgroup of order d. Okay, it means suppose order of g is n, and you have given some d divides n, then there will be a unique subgroup, say H, whose order is d. Okay. Now, one more thing. Okay, this is saying somehow slow. Okay. So, we discussed what is isomorphism. Okay. So, two groups will be isomorphic if there is a one-to-one correspondence between them and that correspondence preserve the group operations. Okay. So if G and G dash, two groups are isomorphic, then we can have some kind of similarities between them. Like they will have same number of elements, that is their orders will be same. And if they are infinite, then again, in infinite cases, you have again two subcategories. Like an infinite an infinite set can be either countably infinite or uncountably infinite. Okay, so if G and G dash both are infinite, then either both are countably infinite or both are uncountably infinite. Okay, it can't be a case like G is countable and G dash is uncountable. Okay, if they are isomorphic, so you will have this type of similarity. Okay, and they will have same number of elements. And yep, one more thing. Uh, if G and G dash are isomorphic, then you will have some one-to-one correspondence between them. So actually, you will have a one-to-one correspondence between their generators also. Okay, that is if G is generated by X, then G dash is generated by phi image of X. Okay, actually, phi of G is G dash. Okay, because phi is an onto map. Okay. So this is how you can have a one-to-one correspondence between their generators also. Okay. Now, one more thing. If we have a cyclic group, then obviously it will be generated by some elements. So how many generators will be there? Okay. So my question is, what is the number of generators in a cyclic group? So if the cyclic group is isomorphic to Z, or if the cyclic group is infinite, then you will have two cases. If G is cyclic, then G can be either infinite or G will be finite. Okay. So in both cases, what will be the number of generators? So if G is infinite, then G will be isomorphic to Z. And how many generators are there in Z? Only two, 1 and -1. Okay, because we can say every integer can be written as some integral multiple of 1 and as well as integral multiple of -1. Okay, so that's why any infinite cyclic group has two generators, exactly two generators. Okay, so if you have an infinite group which has either one generator or like suppose in statement like there can be generators, number of generators other than 2, then you can't say that the group is cyclic. Okay. And what if the group is finite? So in case of a finite cyclic group, what will be the number of generators? So if the group is finite, so this will be isomorphic to Z over NZ. So we need to find number of generators in this group, Z over NZ. Okay. And what are the form of generators? So this is given by the statement. So this one, if G is a finite cyclic group of order n, then number of generator is given by phi n. This phi is Euler's phi function, okay, which is defined like this. So basically this phi n is cardinality of those A such that this A is between 1 and n minus 1 and GCD of order of x and A, this is 1. Okay. So any doubt here? This phi is actually Euler's phi function, and you know how to calculate its value. So phi of 1 is defined as 1, phi of 2 is 1, and what is phi of p to the power k? Phi of p to the power k is p to the power k minus p to the power k minus 1. Okay. If p is some prime number, okay, and phi of mn, this is phi of m, phi of n, if m and n are co-prime. So if you have some natural number n and you need to calculate its phi value, then how to calculate? You will use the fundamental theorem of arithmetic. Okay. And using these results, you will calculate what will be its phi value. Okay, we will do some examples for this. So we will like discuss this in more detail there. And last result,
So, ma'am,
yes.
I have a question here. Do we have any
Mhm.
proof of this formula, like number of generators of G is fine? Do we have any proof for that?
Yes, we have a proof for this, and actually the proof is discussed by our professor in lectures. So you
Okay,
can
so I
refer week
have
three's
one
lecture, and you will get the proof
question.
there. Okay.
Okay, I understand.
Uh, okay. And if G is a cyclic group, and we are discussing about divisibility here, so this should be finite. Otherwise, we can't discuss about this. So if G is a finite cyclic group, then we have this equivalence, like these are some necessary and sufficient conditions. So if G is a cyclic group, then for every positive divisors of order of G, there exists unique subgroup of order of D. Okay, like if D divides order of G, then there will be exactly one subgroup of order of D, and if D divides order of G, then there exist exactly phi of D elements of order of D. Proof for these statements, again, you can find in lecture. Okay. So let's come to some problems. So this is first question we will discuss today. So here we are taking the non-empty set as Z. Okay. So this Z is a set which is claimed to be a group, and the binary operation phi is defined by this rule: A star B is A plus B minus 1. Okay. Then we need to check that Z star is a cyclic group. Okay, so this we need to discuss. So how to do it? So first we need to check whether this is a group or not. Okay. So this Z is our non-empty set, and the binary operation star is defined by A star B is A plus B minus 1. So is it a group? So if this is a group, we need to check four axioms, like whether this operation is closed or not. So this is closed. Why? So this star is defined from Z to Z. Okay. So if A and B both are coming from Z, then A plus B minus 1, this will be an integer again. So yes, we can say that phi is closed. Secondly, phi is associative. Okay, so yes, we need to check the associativity of phi. Why? Uh, See, generally associativity and commutativity, we write this like obviously if we take usual operations, okay, but here this star is not the usual addition or multiplication. This is an operation which is defined differently. Okay, so we need to check whether this is associative or not. So can you check?
Okay, ma'am, just 2 minutes.
Okay, sure.
Yes, ma'am, it is associative.
It is associative. Okay, you can take any three elements, say A, B, and C, and you can check A star B, and then star C is same as A star B star C. Okay. Third, whether there exists an identity element. So we need to find some identity element E if A star E is A and the same as E star A. Okay. So consider this. If A star E is A, then what will be the value of E? So A star E is A plus E minus 1 by the definition of star. This is A, or we can say E is 1. Okay. So here the identity element is 1. Okay. Now, uh, what if I ask this Z, this forms a group under which operation? Plus or minus? Sorry, plus or some multiplication. This is not minus, actually, this was fill in the blank. So either addition or multiplication. Under which operation this Z forms a group?
Addition.
Addition. Under multiplication, it doesn't form a group. Okay. So under addition, it forms a group. But what was the identity there? 0. 0 is additive identity. But here we are taking E as 1. Okay. Because we changed the binary operation also. Okay. So this is why like I said, we need to check the associativity too. Okay.
Okay, ma'am.
Okay. Now, what is the inverse? So for A belongs to Z, inverse of A will be some A inverse such that A star A inverse or A inverse star A, this is identity, which is now 1. But what is A star A inverse? This is A plus A inverse minus 1. Okay. So if A star A inverse, this is identity, that is 1, then A plus A inverse minus 1, this is 1. So what is A inverse? A inverse is 2 minus A. Okay. So this is inverse of elements. Now we can also check that this group is commutative. Okay. Because whenever we will take B star A, so that will be B plus A minus 1, which is same as A plus B minus 1 or A star A. Okay. So this group is commutative or abelian also. So till now, we discussed that this group, uh, this algebraic structure, Z star, this is a group. Now, we need to check whether this is a cyclic group. So, this will be cyclic if we have some generator in this. So, can you think about the generators?
I think, ma'am, the generator is 2 or minus 2 maybe.
2 and minus 2. Okay. Why?
Mm, or maybe, ma'am, it is 1 or minus 1, same as Z.
Okay. So, but how to proceed? Like, how to prove it?
Uh,
Yes, 2 is a generator. And if 2 is a generator, then inverse of 2 will be a generator. So you need to find what will be the inverse. Okay, under this. Uh,
yes, ma'am.
okay, I will discuss. Okay. So how to check? So suppose say A is generator of Z star. Okay. Then any X belongs to G can be written as A to the power K, right? For for some integer K. Okay. Now, what will be A star A? That is, what is A square? A star A is A plus A minus 1. That is 2A minus 1. What is A cube? Which is 2A star A, we can say. So what is this?
Just 3A minus 1.
3A minus 1 or minus 2?
Um,
Wait. I should write it as A square star A. Okay, because A cube will be A star A star A. So this is actually.
3 minus 2.
Okay, so now this will be 3a minus 2. Okay, because this is 2a minus 1 plus a minus 1. So this will be 3a minus 2. What is a4? A4 will be 4a minus 3. Okay, and this is how we can proceed. Okay, so what will be a to the power k? A to the power k will be c. Uh, like the power is coming in the multiple of a and minus a number which is one less than the power. So this will be k ka minus k minus 1. Okay, so
Okay, ma'am. Ah,
for a equals to 2, what will be 2 to the power k? If k equals to 0, so 2 to the power k will be 1 if k equals to 0. And what will be 2 to the power k if k is greater than 0? So if k is greater than 0, um, what you will get from here? This is 2a, uh, so this is 2k minus k plus 1. Okay, so this will be k plus 1. Okay, and what will be 2 to the power k if k is less than 0? So again, yeah, if k is less than 0, no problem. You will have k plus 1 again. Okay, but just here, k is positive and here k is negative. Okay, so see, if k is greater than 0, if k is greater than 0, then you will get some k plus 1. So k is greater than 0 means when you will take k is 1, you will get 2 to the power k is as 2. For k is 2, you will get 2 to the power k is 3. Okay, means for k greater than 0, you will cover all positive integers. Okay, similarly, for k less than 0, you will cover all negative integers. Okay, it means every integer can be written as 2 to the power k. If the integer is 0, it's like if the power is 0. Okay, fine. So 1 can be written as 2 to the power k. Here you will get which kind of elements? So plus 1. So you will get here uh, 2, 3, 4, and so on. And here you get only 1. And here you will get less than 0 means minus 1. So you will get 0. And for minus 2, you will get minus 1, minus 2, and so on. Okay. So this is how you covered all the integers. So that's why you can say that this Z with respect to this binary operation star, this is generated by 2. Okay.
but ma'am, 2 की power k is always positive, and k
2 to
has
the
to be
power
greater than
k is
minus
always
minus
positive.
1.
Uh, see, we are taking all 2 to the power k, all integral values actually. All integral powers of 2. Wait, when we deal with this z plus and we say that this is generated by 1, okay, then we say this can be written as n into 1, okay. So this is for all n belongs to Z. Otherwise, if you like here powers are basically multiples. Okay. So 1 to the power k is basically kn if we are taking additive operation. Okay. So if you take only positive integral values for k, then you will cover only z plus. Okay. So for z plus also we take negative integers also, right? So similarly we will take negative integers here too. Mm, Is it clear or any doubt?
Okay, ma'am. I understand.
Uh, like, is this clear or I need to explain this more?
No, ma'am, I was just saying that 2 की power k is always greater than 0, so k has to be greater than -1 in the third case.
Uh, 2 to the power, okay, now I got your point. 2 to the power k is always positive.
Yes, ma'am.
Whenever you will take k less than 0 or k greater than 0. You want to say this, right?
Yes, ma'am.
Okay, got it. Like for k greater than 0, you will take 2 to the power k, and for k less than 0, you will get 1 over 2 to the power k, like this, or say k dash. For k dash and k both are positive. This is what you are trying to say, I think. Am
Um,
I getting your doubt?
um, uh,
So this is
how
your
can I?
doubt now. Like 2 to the power k is always positive. So either this will be 2 to the power k or this will be like 1 over 2 to the power k dash. So here k dash is greater than 0. So in both cases, 2 to the power k is greater than 0. This is what you want to say.
Yes, ma'am.
See, but actually, we are not taking 2 to the power k like 2 into 2 into 2 up to k times. So this is the usual meaning of power, what we understand in arithmetic. Uh, but this is not the meaning of power here. Okay, this 2 to the power k doesn't mean 2 into 2 into 2 up to k times, where this into or this product is the usual multiplication. 2 to the power k means 2 star 2 star 2 up to k times. Okay, this is the meaning actually.
But still, it will be greater than, I think,
No,
0.
if you take this 2 star 2 star 2, then this won't be greater than 0 always. This will be greater than 0 if you stick with this meaning. Like if you take usual multiplication, then only you will get positive. But if you take star binary operation, then you won't get it. Okay, fine. So what will be 2 square? 2 square will be 2 star 2. Uh, and one more thing. Okay, fine. Let's do it. What will be this? Whenever you will take 2 square, 2 cube, or like anything like 2 to the power 10, you will get positive integers. I agree. But you will take 2 to the power k, where this k is negative also. Okay, so you need to consider some 2 to the power minus k type of things also. Okay, so this will
Okay,
give
okay.
you negative integers.
Uh, Sorry, ma'am. I thought my mind was distracted because of I was thinking about the graph of 2 to the power k. So that's why.
Okay, okay, okay. No, no, no.
Because first time I'm studying about group theory, so that's
Okay,
why.
no problem. But still, just one thing you need to keep in your mind. Uh, Normally, by 2 to the power k, we means we are multiplying 2 to itself k times. But here, 2 to the power k means we are operating 2 to itself uh, under the operation star, not the operation multiplication, which we use in elementary classes. Okay, operations are different.
Yes,
First
ma'am.
thing, and secondly, 2 to the power k. So here k will be positive and negative both. Okay, so for positive, if you take k greater than 0, you will get 2, 3, 4, 5 up to like positive infinity. Okay, so if you take k greater than 0, you will cover these integers only. If you take k equals to 0, you will get the integer 1. But what about 0 and negative integers? So to cover 0 and negative integers, you need to take k less than 0. Okay. For example, I'm taking 2 to the power minus 2. So what this will give you? 2 to the power minus 2 means 2 to the power 2 and then like minus you can say. Okay, so you will get a minus from here also. Okay, so this is why you will go to negative integers.
Okay, ma'am.
Okay.
Yeah.
Mm, wait. Uh, okay, so let's calculate this 2 to the power minus 2. What will be the value?
Um, 4 in 1.
See, don't write it 4 inverse. Okay, this is what
So
I
it is.
was saying repeatedly. Okay, this is not 4 inverse.
No,
This
I mean
is 2
the
star
inverse of 4.
2 and then inverse. And this inverse is not reciprocal. Okay,
Oh, sorry, sorry.
inverse we gave by this. A inverse is 2 minus A. A inverse is not 1 by A here. Okay,
So
so both are
I
different. Okay, so 2 star 2 will be 2 plus 2 minus 1 means
yes, ma'am.
3.
Then
So this will be
3
3
inverse.
and then we have inverse. So see, here 2 square is 3, not 4
Yes, ma'am.
because operation is different. Okay, now what is 3 inverse? 3 inverse is not 1 by 3. 3 inverse will
2
be
minus
given by this.
2 minus 3 and
A
minus 1
inverse,
also.
है ना? A inverse is 2 minus A. So 3 inverse will be 2 minus 3. That is minus 1. So this is how you covered this integer minus 1. Okay.
Okay, ma'am.
So similarly, you can cover this minus 2 if you take 2 to the power minus 3. So 2 to the power minus 3 is not basically 1 upon 8. Okay. No, this is not. Operations are different. Whether you are dealing with power, whether you are dealing with inverse. These are not the usual operations mm, from elementary classes. Okay.
Okay.
So is it clear now?
Yes, ma'am.
Okay. Next question. We need to do some generators kind of thing also. Okay, so find the number of generators of the following groups. One is Z over 27Z. Second is Z over 40Z. And third is unit of Z over 10Z. Okay, so how to do it? So the first one is Z over 27Z. Okay. So wait. This can't work here actually. And okay, we'll discuss this separately. um, Number of generators won't be a cyclic group always. Fine, I'm seeing this is a cyclic group. Okay. So Z over 27Z. How to do it? You can recall if G is a finite cyclic group, of order n, then number of generators of G is phi of n. Okay. So we need to calculate phi of 27. So what will be phi of 27? 27 can be written as p to the power 3. Okay. So this will be, what is phi of p to the power k? Phi of p to the power k is p to the power k minus p to the power k minus 1. Okay. So this will be 3 cube minus 3 square, that is 27 minus 9. So this will be 18. Okay.
Okay.
Secondly, let's take it. I'm not going in detail. Fine. I was telling about fundamental theorem of arithmetic. So what's that? The fundamental theorem of arithmetic says that whenever we have a natural number, say we have a natural number n, we can write it as p1 to the power r1, p2 to the power r2, say pi to the power ri, where pi's are prime numbers and this ri's this belongs to z plus. Okay, so it means we can factorize a given natural number in multiplication of powers of prime numbers. Okay, so here we have a number which is 40. So 40 can be written as, what will be its prime factorization? 2 cube into 5. Okay.
Hello? Yes, ma'am.
Okay. So here the group is Z over 40Z. So what will be the number of generators in this? That will be phi of 40. So we need to consider phi of 40. Okay. So whenever you will have a random number and you have to calculate that's phi image, then what you will do? First, you will write that number in prime factorization form like this. Okay. And then you will apply this. Phi of mn is phi of n if GCD of m and n, this is 1. So why we use this theorem? Because here these term, all the terms are relatively prime. So this is the meaning of writing a given number n in prime factorization form. Okay. So what will be phi of 40? This will be phi of 2 cube into 5. This will be phi of 2 cube, phi of 5. We can break it because 2 cube and 5, these are co-prime numbers, because no two prime numbers uh, can have a common factor other than 1. Okay. Now
For
for
example,
this phi of 2 cube, you can again use this formula, and this will be 2 cube minus 2 square, and what will be phi of 5? So phi of p, this is p minus 1. These all formulas are discussed in lecture videos, so you can refer that. So phi of 5 will be 4. So what will be this? This will be 8 minus 4, that is 4. 4 into 4, that is 16. Okay. Mm, hmm. Now write this also. Units of z over 10z. So what will be number of generators in this? So what is this? Union of 10 z over 10z. It means the unit elements of these group. So how to find units of z over 10z? Uh, these are some results which were discussed in lecture videos. Fine, no problem. I will write it. Units of z over 10z are, simply I can write it as a such that a is less than or equal to 10 minus 1, or simply I can write 9, and GCD of 10 and a, this is 1. Okay. Means number of units of z over 10z, this is again pi of 10. Okay. So what is phi of 10? Phi of 10 is phi of 2 into phi of 5. Phi of 2 is 1 and phi of 5 is 4. So this is 4. Okay. So how many elements will be there in uh, units of z over 10z? There will be only 4 elements. Okay. And what are those elements? So how to write it? Z over 10z. So starting from 1 to 9, you will write all those numbers which are co-prime with 10. Okay. So 1 can be written, 2 we can't write 2, okay? Because 2 and 10, they are not co-prime. 3, 4 can't be written. 5, again, that cannot be. 6, no. 7, yes. 8, no. 9. Okay, so these are that 4 elements. Okay, so this is the unit group of Z over 10Z. Um, okay, just wait. Okay, so is the question clear?
Yes, ma'am.
Okay. Actually, I wanted to discuss whether this is isomorphic to Z4 or Z2 cross Z2, but that will require some results which are not yet discussed in lecture. So that's why I changed the question a bit. Okay. So this was my motto actually, like how we can form a unit group. Okay, so this is the way. Now come to next question.
Excuse me, ma'am. Like
Mhm.
when we are saying units means the units means by that a whole group will be generated.
The whole group can be generated? No. See, uh, what is the original group? Let me use
Uh,
this. The
0 to
original
9,
group
0,
is
1
Z
to.
over 10Z. Okay. This is a group under which operation? Addition, but modulo addition. Okay. In integer modulo 10 addition we will take here. Okay. So this is a group. And units means multiplicative units. Okay. If this is a group, then obviously we will have like inverse of every element with respect to the underlying binary operation. So actually, with respect to this operation plus, we will have inverse of every element. But unit means we are considering multiplicative units. And what is the multiplicative identity here? That is 1. So A is unit if there exists some B belongs to this Z over 10Z. This is again in Z over 10Z. So A will be unit if we will have some B in the same group such that AB is 1. Okay, AB and BA, they are same because the group is commutative actually. Okay, so this is the meaning.
Okay, I've got it. Can we draw the composition table and we can see here, like if so that it will be more clear. Like we are getting one here
Yes, you
with the
can
that,
say, but wait, actually this, uh, see, Z over 10Z, this is a group with respect to multiplication, but unit group Z over 10Z, its unit group, this is this is a group under multiplication operation. So you will find the table, but you need to change the operation. Okay. So you will have these 4 elements, and under multiplication you can find the composition table. So I think you can do it. It won't be such tough.
like 3 into 7 is 21. 3 sevens are 21, and mod 10 will be 1.
Yes.
So with means a single element also we are getting, then it will be considered as unit, no? Like
Single element, sorry.
within the group, otherwise we can say its inverse exists, like something like this
Mm,
units are actually I'm not getting, like I'm understanding, like the elements are 0 to 9 in the Z
mm,
mod 10Z.
mm,
Now when we do the multiplicative operation, so we have to see
mhm.
that the corresponding to which elements we are getting 1 by mod Z, so that elements will be considered as units, I think so.
Yes, yes. And actually this GCD of 10 in A is 1. So this condition is equivalent to that. So what's the doubts now? Actually, uh, in Z over 10Z, we have 10 elements. All has inverse, but with respect to addition. Okay, when you take identity as 0, which is additive identity, you will have additive inverse. But uh, whether every element has multiplicative inverse? No. Additive inverse? Yes, we have for each element. But we have only 4 elements, or we can say we can have only 5 of n elements which has their multiplicative inverse. Okay. So in the group
Five,
Z over
four,
10Z,
so that only I'm saying, like units will say that that elements whose inverse exist, no? Multiplicative
yes,
inverse exist.
yes. Like
One more thing
you
here.
can see. Mhm.
Uh, is there like the number of units of Z over 10Z is same as generators of Z over 10Z? Number of generators of Z over 10Z.
Yes,
Because both are 5 of 10.
yes, both are same.
So is this like true for all
Yes, this
cases,
is
like
true.
for any?
Numbers will be same.
Okay, okay, then. But why do we call this unit? Like, what does the word unit mean?
Because this is a collection of all multiplicative units.
Okay, okay. I got it.
Okay, and actually, these are the inverse. 1 is inverse of itself. 9 is, okay, sorry. 9 is again inverse of its own. And 3 and 7, they are inverses of each other. Okay.
Ma'am, I have a question here.
Mhm.
How many?
Yes.
What is the number of units in Z? Only Z. I mean, what is U of Z?
U of Z. Okay. 2.
Two.
1 and minus
And
1.
yes, 1 in minus 1. 1 in minus 1. Okay. Because whenever we like this U or the like unit group, it means we are collecting only multiplicative units. So in Z, we can have only 2 elements which can have multiplicative units, 1 and minus 1, and both are inverse of their own. Okay, 1 into 1 is 1, and minus 1 into minus 1 is 1 again. No other element can be there. Like if you have A belongs to Z and A is not equals to 1 or minus 1, then you can't have A into B such that 1. Okay. Like if this A is 2, 3, 4 or anything else, then you need to consider fractions. Okay. But fractions can't be in Z. So that's why it has only 2 units. Okay.
Uh, but we can't calculate this using the formula, na? Phi, by using the
The
quotient.
formula phi works only for finite groups.
Okay, okay, okay. I got it.
Okay.
Yes, yes.
And also we are saying number of generators means we are discussing about cyclic groups. So here this Z
Yes,
over
yes.
10Z, this is a cyclic group. If you take any like non-cyclic group, then you can't say like simply what is phi of D there. Okay. And one more application of this, phi of D or say phi of N. So this is basically
Ma'am, one more question. Like,
Yes.
when we say primitive root, then also it is a generator only.
Hmm.
Is it
Uh,
same?
in multiplicative, like you are coming to fields.
Primitive root, I'm asking. When we say it is a
Okay.
primitive root, like, so means with that element, whole group can be generated.
Yes. Okay, but actually that is more related to field kind of thing. But again, like if you take a field, then F star with respect to multiplication, this is again a group. So this is multiplicative group. So yeah, you can like apply that uh, concept here. Okay.
One more, I have the doubt. Actually, I was in the way, so I couldn't ask at that time. Like,
Okay.
when we in the beginning, you have discussed like the order of the cyclic group for finite and infinite, no?
Mm-hmm.
So for infinite, we have only 2, 1, and -1. That will be over integer.
Generators, no? Generators of or
Generator.
order of cyclic group. Generator, right?
Uh, and for a finite group, I was actually I had the doubt, so I couldn't ask in between because I was in the way. So I was
Okay.
listening, but actually I was driving, so I couldn't ask at that time.
Okay, okay. You can ask now.
Could you explain that part in short, like in the beginning?
Okay. So actually, is if G is infinite, number of generators is 2. That is plus and minus 1 in case of Z, or like isomorphic image of plus and minus 1. Plus 1 and minus 1. Okay. And if G is finite, finite cyclic group, then this G will be isomorphic to some Z over NZ for some n belongs to Z plus. Okay. So number of generators will be phi of n. Okay. Finite cyclic group will be isomorphic to Z over NZ, and number of generator will be phi of that n. Simple.
This is the Toshin group. Like it means ki the within the set, which numbers are co-prime with number of elements co-prime with that
Yes.
n.
Co-prime with that n,
So
and obviously
this
we
Toshin
will.
function is something magic. Like at once it gives this formula. I don't know how they have thought this key, because for me it's just like a magical word. Like the how the person has thought. Like if in a general way we have to see, so we are going to count each and everything. But I don't know how they have correlated this Toshin function that at once they get this the formula, like no you're discussing
Yeah,
p into p
I.
minus 1 or p square minus p, something like that. So I think it's just like a magic or something, or I don't know, is there any derivation part, or just it is a simple
Actually,
proof
there
must
is
be
a
there
derivation
that
part. There is a derivation part actually. Actually, this is covered in video lectures also. So whether you can
I'll go through it.
like
Actually, I have not gone through in details. I'll go through, ma'am, that part.
okay, sure. Otherwise, like we will not have much time to discuss questions. Okay, we have like at most 40 minutes remaining, so that's why. Okay, so next question. Okay, so one thing, do you know how to calculate GCD of two numbers if the numbers are bigger, and if you like using division algorithm basically?
Yes, ma'am.
Okay, fine, because there are some questions related to this in this week's assignment. So I hope you can do this. Like you can calculate GCD of say 172 and 20. So can you calculate this?
Yes, by
Yes, ma'am.
Euclid division we can do.
You can do it. Okay, fine. So actually this is simple because numbers are small, but if you have a number of 4 or 5 or 6 digits, then uh, Euclid's algorithm is actually much helpful. Otherwise, prime factorization could be difficult. Okay. So next, okay. Consider a statement if order of a group G is prime, then G is cyclic. So is it true? Um, how to do this? Suppose we have a group and it has P elements where P is a prime. Yes, you want to say something? Or you want to guess whether this is true or false?
Ma'am, because
It is
every
true.
prime number is finite, so G must be cyclic.
Okay. So yeah, actually this is true, but how to justify or how to prove that yes, this is a true statement? So
Like, ma'am, like for prime, I think every units will be, every elements will be the unit, no?
every element or uh, okay,
Every
every
element of
element.
the, like, or if it is prime, like order is prime,
Mhm.
if Z mod PZ I'm talking about.
Okay.
So every element
Uh,
will be the generator.
every element will be the generator.
Is it wrong?
What about zero?
No, apart from zero, units I'm talking about. Means zero we are
Yes,
neglecting.
yes, yes. Every unit will be generator, right? That's true. So if order of G is prime, then you will have P minus 1 units, exactly P minus 1 unit elements, okay? And the remaining one element that is 0, which is not multiplicative unit, basically. Okay, so yeah, that is true. So, but fine, you can say like all units are generators. So actually to prove that G is cyclic, we just need one generator, okay? And that is sufficient. So you can also say that order of G is prime and P is greater than or equal to 2, obviously. So we can have an element which is other than identity in G. Okay, so that's why order of A, this will divide order of G, okay? That is order of A divides P. It means order of A can be either 1 or P because P is a prime, but A is not equals to identity. So order of A cannot be 1. Therefore, order of A is P. Okay. So this is how we can get an element of order P. Okay. And this element will generate the uh, entire group G. Okay. And actually you can say like order of A is P. So this A to the power 0, leave it not from 0, start from 1. A cube, or like if I write just this A square. So that's why we can say if p equal to 2, then what will be the case? A to the power p. So these are exactly p elements, and this a to the power p, this will be the identity. Okay. So if order of A is P, then this collection A square up to A to the power P, this will have exactly P elements. Why? Because if any two elements are same, so then we will have A to the power I is A to the power J. That means A to the power I minus J is identity. And if without loss of generality, we say I is greater than J, then we will have something I minus J, which is less than P. And when you write it as power of A, you will get identity. It means you can have something less than P, which can be power of A, which is a contradiction. So no, this is not possible. Okay, so this is exactly P different elements. Okay, and G has exactly P elements. So this is how you can say that this subgroup generated by A will cover the whole group G. Clear? I know this is a
Yeah.
trivial kind of thing somehow, but still in group theory, we need to write systematic proof. Okay, we need to consider each and every case.
Uh, Excuse me, like one question, like
Mhm.
for the cyclic group, you have said order of A must divide order of G, no?
Mhm.
So before that, is it correct, no? Or
Yes.
wrong? So before that, what we have taken the example Z mod 10Z.
Huh.
So order of G will be 10.
Yes.
And what the we have generated like a cyclic group, so with the four elements.
That group is different.
Okay.
Both are different groups. Both have different operations.
There we have done with the multiplication case, and in the first we have done
Mhm.
with the addition.
Addition case. Yes.
So with respect to addition, we are not going to get the I think inverse, so that's why
Uh, See, in case of Z over 10Z, we have inverse of each element with respect to addition. Each each
is
element of Mhm. Each element of Z over 10Z has additive inverse, but not multiplicative inverse. Only 4 out of those 10 elements have multiplicative inverse also. This is the case.
what will be the order of
And
A in that Z upon Z 10 mod Z
see,
is not cyclic, no? Then
that is cyclic
with respect to plus.
with respect to plus.
So it is cyclic. So what will be the order of A in that?
Uh, what is A actually? A can be anything from 0 to 9 or
Okay,
like
we'll
1
see
to
that
10,
how many
whatever.
times will be added to get 0.
Yes,
That will be that. Yes.
yes. Actually, orders are defined in different ways in Z over 10Z and units of Z over 10Z. Okay. In Z over 10Z, we need to consider A plus A plus A up to how many times so that we can get 0. And in units of Z over 10Z, we need to consider A into A up to how many times so that we can get 1. So this is the difference. Okay. Both are different kind of groups. Next question. Which of the following groups are cyclic? First, Z star with multiplication. So in this question, we are considering some unit groups. Okay. and Q star, R star, and C star. Okay, so these are 4 cases. So there were 4 groups, Z, Q, R, and C, which forms a group under addition. And here we are taking their uh, group of units with respect to multiplication. Okay, so which is cyclic and which is non-cyclic?
Pardon, ma'am, Z star we have taken as non-zero elements or units.
Star means unit.
Okay.
So first one, what is this? Z star dot. So Z star is basically units of Z, which is 1 and -1 simply. Okay, so yes, this is cyclic. Now come to this Q star and dot. What is this? What is the difference here? So first, what is the group actually? So this is basically the set of all non-negative rationals. So this is what you were asking, whether star represents units or non-zero. So actually star represents units, but in case of Q, in case of R, all non-zeros are units. Okay. So in that way, this star reduces in collection of non-zeros. That's it. Okay. So this group Q star dot, can this be cyclic or not? So first, this is collection of all non-negative rationals. It means this is infinite. Okay. So this is clear that Q star is infinite. And if this is infinite, then it will have so suppose Q star is cyclic, then this Q star will be isomorphic to Z with respect to plus. Okay. Now check whether they are isomorphic or not, whether their elements have one-to-one correspondence or not. So okay, see this -1. This -1 belongs to Q star, and -1 to -1, this is 1. That is order of -1 is 2. Okay, that is Q star has an element of order 2. But Z does not have any element of order 2. So Q star is not isomorphic to Z, but there cannot be any infinite cyclic group other than isomorphic to Z. So Q star is not cyclic. Clear? So this is actually the fact if two groups are isomorphic, they will have same number of elements, and they will have same possibilities of order of elements, and for any given order there will be same number of elements which has that order. Okay, is it clear or should I repeat? Is the question clear?
Yes, ma'am.
Okay. Third one, we had this R star dot. So this is again non-cyclic. We can give similar argument here, and one more thing which we can give other than uh, this fact that R star has an element of order 2, R star is uncountable. Okay, like this justification can also be given that R star is uncountable, but Z is countable, countably infinite actually. Okay, so if R star is cyclic, it will be isomorphic to Z, but uh, uh, an uncountable set and a countable set cannot be isomorphic. Okay, so this can be another justification also. Now, fourth one is C star. So is this cyclic? Again, if this is cyclic, this will be isomorphic to Z, but Z cannot have an element of order 2, and even C star has an element of order 4 also. Okay, like iota minus iota, they have order 4. Elements of order 4 also. So C star is again not isomorphic to Z. So you can say C star is non-cyclic. Okay.
One question, ma'am. In the second question, I have a doubt.
Mm-hmm.
So, uh, you said that Q star has all non-negative rationals, but then you supposed -1 belongs to Q star, but -1 is negative.
Sorry. Non-negative. Uh, Thank you for pointing it out. All invertible rationals, or I wanted to write actually all non-zero rationals. Not non-negative, non-zero. Okay, that was a mistake. Thanks for pointing it out. Okay, one thing, actually, there is a beautiful result. So, if you have, do you know what is a field?
Yes, ma'am.
If, okay, so let F be a field. So if F is a field, then all the elements other than the additive identity will be invertible, will have multiplicative inverse. That is this F star. This is the collection of A belongs to F such that A is non-zero. So every finite subgroup of F star is cyclic. Okay. So if you take this C star, so here C is a field, and C star means or like similarly, you can write this that belongs to C such that this Z is non-zero. So every finite subgroup of C star is cyclic, but C star itself is not cyclic. Okay, so actually here we are taking just fields. They can be either finite fields or infinite fields. So if you have finite fields, then yes, F star will be cyclic. But if F is infinite field, then F star will not be cyclic. But in both cases, finite and infinite, every finite subgroup of that will be cyclic. Clear?
Excuse me, ma'am. Like the very first one here, what we have solved the question
Mhm.
for rational one, Q star over isomorphic to Z star. So its order you have written as 2, and
Q
which is
star
not
is not isomorphic to Z star. I wrote, suppose if possible, they are isomorphic. But this is not a statement that they are
so
isomorphic. Okay.
that only I want to understand. Like how we have said like -1 and -1, that is order 2, and in Z it doesn't order 2 not belongs to that. I'm not understanding that part.
Okay. So is this clear that -1 belongs to Q star and -1 has order 2?
Yes.
Okay. I agree that -1 belongs to Z, but uh, see, we have this Q star with multiplication and Z with addition. Okay. -1 belongs to both. -1 belongs to this, and in Q star, order of -1 is 2 because -1 into -1. When we operate -1 to itself 2 times, we will get the identity. Okay. But -1 belongs to Z. This is true, but insufficient to give -1 plus -1 is identity. Here identity changes, here group operation changes. Okay, so -1 is an element of infinite order in Z. Actually, Z has only the Z with respect to plus, identity will be 0. So here order of 0 is 1, and for all A belongs to Z, if A is other than identity, order of A is infinite. Z has exactly one element of order, some finite number.
Yes,
Clear?
understood, ma'am. Now understood. Thank you, ma'am.
Okay. Okay. So is this clear? If we have a field, then every finite subgroup of F star will be cyclic. But F star, this can be either cyclic or non-cyclic. Okay. So we can also say like if F is finite, then F star is cyclic. If F is infinite, F star is non-cyclic. Okay, and here you can have one more statement. If every finite subgroup of F star, or if you write, say, some group G, and then you consider unit of this. So if you say every finite subgroup of unit of G is cyclic, then is G cyclic? So no, you can have a counter example because G can be either R, G can be C, G can be Q, okay? So this statement is again false. Okay. Now I'm giving another statement. Check whether this is true or false, or I can split it in several cases. Okay, fine. So let G be a group and G has exactly one generator. Then what you can conclude about order of G? Order of G is infinity. Order of G is 2. Order of G is less than 2. Order of G is greater than 2. What you can say? So G has exactly one generator. We don't know till now whether G is finite or infinite. So there can be two cases. G is finite or G is infinite. So if G is infinite, then G will, as we are already considering generator, so G will be cyclic. This is understood. Okay. So if if G is infinite, then G is infinite cyclic group. So G will be isomorphic to Z, but Z has two generators and they are 1 and -1. So G cannot be infinite. Okay, because G has exactly one generator. So this is false. Now, if G is not finite, then G will be, if G is not infinite, then G is finite and G has some generator. So G is finite cyclic group. Okay. So G is finite cyclic group. So we can say G is isomorphic to Z over NZ for some n belongs to Z plus, right? Again, we have number of generators in G, okay? And if G and Z over NZ, they are isomorphic, they will have same number of generators, okay? Number of generators of G, this is same as number of generators of Z over NZ, okay? But number of generators of G, this is 1. And what is number of generators in Z over NZ? This is phi of n, okay? Therefore, we get phi of n is 1. And phi of n is 1 if n is equals to either 1 or 2. Okay. Therefore, order of G is less than or equals to 2. So, actually these two can be true, or if I want to merge this, then you can say this is true. Clear? Less than or equals to 2 means obviously we cannot go to negative, we cannot go to 0 because we are taking non-empty set. Okay, so less than or equals to 2 means either 1 or 2. So is this clear? Like I'm saying here, if phi of n is 1, then n is 1 or 2? Can you imagine this, or we need to discuss this in detail? Or this is clear?
One like
It's clear.
phi of n equal to 1. This I'm understanding like n equal to 2. Like
Mhm.
phi n equal to 1 means ki number of elements co-prime with 1.
Co-prime to 1. Mhm.
So 1 is co-prime with 1.
Yes, that is trivial actually.
Means GCD is 1, no? So 1 1
GCD
GCD
is
is
1.
1.
GCD is 1, right?
Yeah.
So GCD of 1 and 1 is 1. Vaibhav, you were also saying something.
It's clear, ma'am.
Okay.
Totally.
Because if you take n is greater than 2, then phi of n will increase. Okay. One thing actually I just remembered, so I'm telling. I'm not going to prove. This phi, this is Euler's phi function. Okay. So this function is neither 1 1 nor on 2. Okay. Like if someone will ask, you can say. Actually, phi of 3, this is 2, and phi of 4, this is also 2. So this is not 1 1. And for on 2, I guess for 14, we cannot have its pre-image. So that's why. Okay. So this is neither 1 1 nor on 2. Next question. Check which of the following groups are cyclic. First is GLNF, where F is some field, and secondly, SLNF, that is general linear group and special linear group over some fields. Okay. So are they cyclic or they are not? So what is GLNF? GLNF means the group of all n by n invertible matrices over the field F. Okay. And SLNF means the set of all n by n matrices with determinant 1 over the field F. Okay. So these two are set of matrices. So obviously they will not be abelian, so they cannot be cyclic. Okay. If a group fails to be abelian, the group cannot be cyclic actually. Okay. So if you have matrices, you cannot have cyclicity there. It means if n is greater than or equal to 2, neither GLNF nor SLNF is cyclic. I'm not saying whether F is a finite field or infinite field. For both cases, GLNF will be set of some matrices. Matrices of order 2 by 2, 3 by 3, 4 by 4, and so on. You will have some matrices, you will have non-commutativity there, you will have non-cyclicity there. That's it. But what if n is 1? If n is 1, then let's do it one by one. What is GL1F? GL1F means all 1 by 1 matrices which are invertible over F. 1 by 1 matrices means single element actually. Okay. So SLNF means all those elements of F which are invertible. It means which are units. So GL1F means F star. Okay. So we know this F star is cyclic if F is finite, and this is non-cyclic if F is infinite. Okay. So GLNF will be cyclic if and only if N is 1 and F is finite. Clear? Also, what about special linear? SL1F. Okay. For greater than 1, this is not cyclic. But what is SL1F? SL1F means the set of all 1 by 1 matrices, means single element, over F, over the field F, such that the determinant is 1. What is the determinant of 1 by 1 matrix? What is the determinant? That is the element itself, no? So we are taking that we need determinant 1. So that can give only the element 1 itself. Okay. So SL1 F is only 1 with respect to multiplication. Okay. So yeah, obviously this is trivial group. This is cyclic. Irrespective to whether F is finite or infinite. In both cases, this will be just 1 because we need determinant as 1. Clear? So SL and F will be cyclic if and only if N is 1. F can be finite and infinite, both. Clear? So
Excuse
we
me,
don't have.
SLN group, you have named something as a symmetric
Special
group.
linear.
A
Special
special linear.
linear.
Okay.
General linear and special linear. Okay. Consider this. Which of the following statements are true? First, a group cannot be isomorphic to its proper subgroup. Second, if there exists an element of order infinite, infinite order in a group G, then G has infinite number of elements of order infinity. You can have another statement. If G has an element of order D, then G has a subgroup of order D, and fourth converse of statement 3, that is, if G has a subgroup of order D, then G has an element of order D. Okay, so let's do it. We have 4 statements and we need to check which is true, which is false. So first, a group cannot be isomorphic to its proper subgroup. What is proper subgroup? Proper subgroup means a subgroup which has at least one element less than the subgroup. Okay, like equality is not there. So can this be true? A group cannot be isomorphic to its proper subgroup?
It is true.
Okay. This is true in case of finite groups. What about infinite?
Uh, okay, if the group is infinite, its subgroup will be also infinite.
True for finite groups. Okay, like if G is finite, then its every proper subgroup will be finite. So what is the case actually? If order of G is n, then order of H will be less than n. It cannot be equal to n. Okay. Then obviously G and H cannot be isomorphic because they have different number of elements. So yeah, they cannot be isomorphic. But I'm saying like what if G is infinite? Because this restriction is not given there. Simply a group cannot be isomorphic dot dot dot. Not a finite group or an infinite group. So for finite group, the statement is true. What for infinite groups? If G is infinite, then when we talk about infinite group, the first group which comes in our mind is actually Z plus. Okay. And what are its subgroups? Its subgroups are dz, where d belongs to z plus union 0. That is all non-negative integers. So you can consider this 2z or 3z or anything like any d belongs to z plus. So z and dz, they are isomorphic. But dz is a proper subgroup of z. Like in particular, if you take this 2z, it cannot have like it cannot have like non-even integers. Okay. No odd integer can be there. In case of 3z, no integer which is not a multiple of 3 cannot be there. So 2z is properly contained in z, or you can say 2z is a proper subgroup of z, but 2z and z, they are isomorphic, group isomorphic. Okay, so the statement is not true in general. Clear? Why they are isomorphic? Yes.
Actually, this question only I was asked. I was going to ask. Like,
Okay.
I'm not.
You can
Like
this,
what I'm thinking, like number of element, like units will be same. 0 will be mapped to 0, and corresponding to every element of 2z, we are going to get the element of z. So I think it will be isomorphic then, because unit, if the unit is unit of 2z is mapped to the unit of z,
I hope in am I hello? Am I audible? Problem. Hello.
yes, ma'am.
Okay. So, but the screen is not visible, I think.
No, now it is visible. I think. Now it is not visible screen.
It is not now. I know. Wait. So actually, I'm not turning on my video. Maybe there may save some internet. Okay, wait. Is it visible now?
No, ma'am, still it is not visible.
Uh, okay, let me try this again.
Ma'am, doesn't matter. Next time we'll continue.
I think yeah, time is over. From this question onwards, we can
Okay.
discuss the next.
What I think for the isomorphic units, I think is mapped to unit only, and corresponding
Mhm.
to every element, I think we are going to get uh, a corresponding element over there. Not exactly equal, but if we are going to map, like one mapping can be done.
Mhm.
Is it correct?
Uh, what did you mean by units? Like multiplicative units?
No, no.
Multiplicative,
Identity. Z.
additive
If I'm
units.
okay,
So
with respect to
all.
multiplication, with respect to that one.
Mhm.
Identity in the like 2z is 0 with respect to
Identity.
addition.
Identity is zero for both Z and 2Z.
So identity is same.
Hmm. Actually, a
So
group and any of its subgroup cannot have different identities. So
okay, so we'll discuss then next time then.
yeah, sure. It can be a homework actually. You both think about what can be the correspondence, and yeah, we will discuss this in next class. Today there was
Ma'am,
some
I have to ask more questions on
network
that. We'll
issues, so
discuss like
yes.
when we look for the isomorphic, no, this idea also I was not getting like in which circumstances we should see the isomorphic relation and how we can think that this particular group will be isomorphic. So there is a lot of issue with that for me. So next time we'll
Okay.
discuss, ma'am.
So, okay, sure. I will include some more questions on isomorphism of groups and
Yeah, ma'am.
we will discuss in detail.
Okay. Okay.
Okay.
Thank you, ma'am. Good night, ma'am.
Okay. Thank you.
Okay.
Thank you.
Thank you, ma'am. Uh,
Thank you.
good night, Vaibhav.